The project we are doing is the binary system. It started in ancient China, but now it is almost in all of our electronics. The binary system uses the base 2 system. That means every number is a multiple of 2. Though when you see a binary number, you only see ones and zeros. These are the core numbers of the binary system. When you see a 1, that means that number is part of the whole number. If you see a 0, that means it doesn't count to the whole number. Also, when reading binary numbers, you must read it right to left. As you can see at the top, I listed like a binary number line. It goes 1, 2, 4, 8, 16, 32, 64, etc. Now let's take the example of 1, 0, 1, 0. Now when you recite a binary number, you recite it from left to right, even though you read it right to left. But in this 1, 0, 1, 0, we know that the first 0 is 1. We know the second number, which is a 1, is a 2. We know the third one is a 4. We know the fourth one is an 8. Now only 2 of those are 1, so only like 2 of them count. So that number equals 10. Since we are doing binary addition, it's a bit different from normal addition. As usual, 0 plus 0 equals 0. 1 plus 0 equals 1. Though 1 plus 1 equals 1, 0. The 1 carries over into the column over. Let's look at this problem, 1, 1, 0 plus 0, 1, 0. 0 plus 0 equals 0. 1 plus 1 equals 0, 1. So I have a carryover into the next column. And in that next column, it's 1 plus 0 plus the carryover of 1. And we know 1 plus 0 equals 1. But 1 plus 1 equals 1, 0. So I write 1, 0. So the answer is 1, 0, 0, 0. Now 1, 0, 0, 0 actually equals, if we look, it's 1, 2, 4, 8. 1, 0, 0, 0 equals 8. Binary subtraction is quite similar to decimal subtraction, though it is slightly different. When doing binary subtraction, the carryover rule still applies. So let's look at the number 1, 0, 1, 0 minus 1, 0, 0, 1. 0 minus 1 does not work because that's a negative number, so you need to borrow it from the next column over. Now I borrow it from this one, and it goes over. But now it's 1, 0. Now 1, 0 would always equal 2. So 2 minus 1 equals 1. So I write a 1 here. But now, in this column, there's a 0 there, not a 1. So 0 minus 0 equals 0. Then the next column, 0 minus 0 also equals 0. And 1 minus 1 equals 0. So the answer is 0, 0, 0, 1. Now if we convert that, it's 1, 2, 4, 8. And so in decimal numbers, that number is 1. Binary multiplication is quite easy because it's almost identical to decimal multiplication. Now let's take the number 11010 times 11. So first I do with multiplying. So it's 0, 1, 0, 1, 1. Now I move to the next column over. And like in decimal multiplication, I put a 0 here, and now I start multiplying. Because it's in the so-called tens columns. So now it's 0, 1, 0, 1, 1. Now I add all of this together. 0, 1, 1, 1. But now it's 1 plus 1. Now I know 1 plus 1 equals 1, 0. So I put a 0 here, put a carryover 1, and 1 plus 1 equals 1, 0. So it's 1, 0. The binary number 1, 0, 1, 1, 1, 0 equals, in decimal numbers, 1, 2, 4, 8, 16, 32. Now we add all the numbers that have a 1 in it. So I see 1 and 32, 1, 8, 1, 4, and 1 and 2. And so all that together equals 46. So the answer to this problem is 46.
Binary division is much like decimal division or regular division that we do in modern days. We have a divisor and a dividend. It's basically 1,101 divided by 11, but reworded differently. We need to find how many multiples of 11 are closest to 11, and that's obviously only 1. So we shall subtract the 11 from 11. Now we are left with 0, 1. It is better to deal with remainders and leave it alone than continue to divide. It's just simpler that way. So we remain it at 1, 0, 0, remainder 1.
The binary system is also used on computers. Computers have many different types of transistors and many transistors. Today I will be talking about the exclusive OR. This is how it's written. Beside it you see something called the truth table. The truth table is the table that tells you whether or not a transistor will turn on or off. Truth tables are unique to the transistor. On this specific transistor, only the 1, 0 and the 0, 1 combination will turn on. The other two will stay off. The symbol of an exclusive OR looks like this. On a side note, did you know that the binary system that we do by hand and the binary system that the computer does, the way we do it and the way the computer does it is different? It's actually called the XOR, not the exclusive OR.